All right, it's 2 o'clock. Let's get started. Today's physics seminar is by Allan Angus. He's native of Canada, where he studied physics and electrical engineering, had a career in telecommunications, and he now lives in Kansas, where, Colorado. Yeah, well, one state off. In Colorado, where he works with a friend of Nick and myself once in a while in Colorado Springs. And so when Janus said you should invite this guy for a seminar, I figured, why not? Let's see what you have to say on Emmy Noether and her theorems and how it influenced the development of particle physics. So
there you go. Just put this on my.
Welcome, Allan.
Thank you. Thank you.
Yes, what people on the recording later against that. Oh. Yeah.
Let's hope that sticks. Can you hear me? Is this working okay? Cool.
All right, and up and down keys.
Okay. So here we go. So as Holger was saying, I'm here today to talk about Emily Noether's theorems. Count them, 2 theorems. Almost everywhere you hear somebody talk about Noether's theorem, they're only referring to the first one. So many people skip over the fact that she actually had 2. And this will get us into the whole idea of gauge. My own interest in Emmy Noether, kind of a thing I stumbled on, interestingly enough. It was about 50 years ago, the start of this month, that I went into physics in first year at the University of Calgary, about a day's drive to the west and 2 days drive to the north from here. And this time of year, when I got into 4th year, 4 years later, I was in a class done along the English style. You only got to see the prof when you needed to. There were no lectures. You got in. He would ask you questions when you proved yourself good enough to, go for an interview. And the first interview I had with him, I had completed a bunch of sort of Jackson style electromagnetics problems for one of the chapters that I selected to do. And I thought that his questions were going to be on, the technical details of EM. And instead, his question to me was, what's the meaning of the A field? And I hummed and hawed. I had to, he gave me a stack of books. This was one of them to go and read. And I pondered through all those things, came back once, and I still didn't have a good answer. I think it took me 2 or 3 times total before I wound up giving him an answer about what the meaning of the A field was. And you will see here as we go along how the A field comes up and all this. Well, this is Emmy Noether. She was born in 1882. Her father was a professor at the University of Göttingen, and Göttingen is, brought many mathematicians and physicists into the world. She had 2 strikes against her as far as getting into Göttingen. One was she's a woman, and back in the day, women were considered just too troubling, bothersome to the men, so she couldn't get registered. Initially, because her father was a prof there in the maths department, she was allowed to audit courses, but not to actually be a student, couldn't get a degree, couldn't be registered. But somehow she came to the attention both of Felix Klein of the Klein bottle and David Hilbert. You may have heard of him. And kind of like Marjorie Stevenson and the crystallographer Kathleen Lonsdale, outside of a very narrow circle, Emmy Noether was, little known. And but again, in 1915, Einstein published his general theory of relativity, and there was a significant problem with the with Einstein's theory. So, having said something about Noether herself, I'm going to jump ahead to how this all gets into the standard model, and then I'm going to jump back into group theory. I'll talk about Noether's two theorems, how they came out of an assignment that Klein and Noether gave to her. And I'll touch very briefly on Lagrangian dynamics, the idea of a gauge and how that plays into the concept of gauge in the standard model. And so here is the whoop-de-doo standard model of particle physics. You'll see on the side here, it's described in terms of the composition of U1, unitary group of order 1, SU2, and SU3. So U1 cross SU2 cross SU3. This applies to the composition of the, let's see, where does this go? Yeah. No, that's not showing up. Anyway, well, the electron and photon interaction goes according to U1. The neutrino W and Z bosons goes against SU2, and the quarks and the gluons are composed out of SU3. So we're going to jump into that now. Here's the digression on groups. Anybody already have a course on abstract algebra? This is going to be like the most simplistic introduction to group theory you ever did have, just in terms of time here. So a group is a set of elements, might be numbers, might be shapes, might be any old thing, and it has an operation. Sometimes the operation is called times, sometimes plus, whatever. And the rules for the group are fairly simple. If A and B are elements of the group, then A plus B also has to be a member of the group. So you have closure, right? There has to be an identity element. So in this case, call it 0. A plus 0 has to equal 0 plus A has to equal A. So when you're adding or multiplying the identity element, and usually if it's multiplication, the identity element is called 1. Here, we're doing addition, and so the identity element is typically called 0. And then we have an inverse. So every element has to have an inverse. If you add the inverse to the element, you get the identity, and that has to work both ways. Those have to be commutative. In general, if A plus B equals B plus A, then you have a commutative group, which is also called an abelian group. We're not saying AB, we're saying, abelian after the mathematician that studied those things. Lots of groups are non-commutative or non-abelian. In general, if you're multiplying matrices, for example, A times B is not B times A. Okay, so that's all I'm going to say about that. The simplest group I know of is displayed here. It's just binary arithmetic. Okay, So you can see right off the bat that 0 is the identity element. You add 0 to anything, you get that back. 0 is, of course, its own inverse, and 1 is also its own inverse. You add 1 and 1 binary, you get 0, right? And so a really simple group. Now, in the following, we're going to be interested in symmetry groups. And so here's a couple of simple symmetry groups. So we have finite and discrete groups if we think about rotations of a square, okay? So if you think about the square and rotating it 90 degrees, let's say counterclockwise, you do it 90 degrees, you can't tell that it's different from what you started with. Now, if you number the vertices, you can see that it's going, flipping from 0 to 1, 1 to 2, 2 to 3, and 3 back to 0. This means it's sort of isomorphic to addition mod 4, right? 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And you could go backwards as well, right? So this introduces the idea of a generator of a group. Here, the operation of rotation is going to generate from the beginning point every element of the group. You're just step, 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 right? Now, we also have infinite symmetry groups, sometimes called a Lie group, after Sophus Lie, a mathematician that published a book in, I think it was 1891, Basic Theory of Infinite Continuous Transformation Groups, and this comes up frequently in Noether's paper of 1918, right? So she often refers to these infinite continuous symmetry groups. So this is sort of going to the Lie U1 group. So with a circle, you have a generator of infinitesimal rotations. So for that circle, you can rotate it any sort of amount of phase, and you still wind up looking at the same circle. A bit of a digression here. In the case of the circle, the area within the circle is called a two-ball. It's a two-dimensional element, and the perimeter is the sphere. So in mathematics, the sphere is the outer shell, I guess, of the ball, and that's a sphere. So what we're looking at here is ultimately going to get us to U1, the symmetry group of unit 1, okay? And inside the circle is the two ball. Now, if I take that square and I plunk it down in the complex plane, and I imagine that at the vertices there are zeros in the plane, this becomes equivalent to a polynomial. And this is a gateway into Galois theory. Évariste Galois studied these symmetric shapes in the complex plane in the context of being able to solve polynomials. And if you're interested at all in that concept, you can see here that you could potentially transform some of the zeros in the plane between one another, and you might get or not get the same result, okay? I invite you to play around with that, with moving I to minus I in any old equation that you could figure out. You will discover that you can't tell the difference between I and minus I in polynomial structures. Well, if we take the unit circle in the complex plane and consider the phase of that, now we're thinking about the U1 group, the continuous symmetry group. When we say a unitary group in this context, we're actually talking about a set of polynomials of a certain order, and or matrices, another way to describe it. U1 being the simplest, you will see that the S in front of the SU2, SU3, demands that the matrices that we're talking about have to be real only. We don't use S in the context of this symmetry group because we need complex numbers. So we have to have a phase associated with the group, right? And of course, this has a generator of an infinitesimal phase rotation to make it interesting for our uses here. So I guess that's all I say about that. So now, what was the problem with GR? It came out in 1915, and suddenly David Hilbert and Felix Klein are going to give Emmy Noether a project of figuring out what went wrong here. So I don't know if you can see that, but on the left-hand side is a tensor for space-time distortion, I guess, movement away from a flat space-time. And on the right-hand side, team you knew there, is the energy stress tensor, okay? You will notice, and I'm not expecting all of you people to understand the tensor structures of GR here. Maybe you do, maybe you don't, but notice first that the tensors all have their indices on the lower part. That indicates that they're covariant matrices. If they had the indices on top, then they would be contravariant matrices. And one of the things about the whole idea here is that this equation is supposed to be invariant as to the frame of reference of the observer. So general covariance is important. That says that you're describing something about the physical world which is independent of the platform of the observer. And in this case, it's supposed to be invariant to the acceleration of the frame of reference of the observer. In special relativity, the idea is that you're invariant as to an inertial frame of reference. You're going to see the speed of light as the same thing no matter how fast you're moving, right? Here, you're supposed to see the same thing whether you're accelerating or not. Well, what's the problem with this? Why did, David Hilbert lose his cookies about this thing? I assume that if anybody in the room here has a physics background, you've probably done that calculation where you imagine a test mass, let's say on the surface of the Earth, and you push it out to infinity. So you will do an integral that computes the total amount of energy or work that you did to take the test mass, say a kilogram, out to infinity. Or alternatively, you let the test mass go from infinity and it falls in, right? Either way, you see a balance between potential energy and kinetic energy. But if you're riding along with the test mass as it falls in, you're just running along a geodesic. There is no acceleration from that point of view. You're in free fall. There's no work on the test mass. If there's no work, there's no potential energy. A whole pile of energy just disappeared from the universe when this equation came out. That's the problem. Einstein tried to address this. This is his equation. And you'll see right off the bat that some of the indices are on the top side. It's violating the principle of general covariance because it has contravariant elements to it. And so Noether saw that this, immediately fails because it lacks this idea of general covariance. Well, here's a current example. Of course, this wasn't known back then, but if you think about the cosmic microwave background radiation, about 3,700 years after the Big Bang, the plasma got thinned out enough that the light could get through. It's no longer being scattered by the density of the elements in that plasma. And the cosmic microwave background radiation, depending on how you think about it, I guess, contains about a ratio of 400 to 1 compared to other photons. I mean, we have light in this room, but the light in this room is not going to permeate every square meter of the universe, right? So the CMB is pretty much all the photons. And at that time, the thermodynamic energy was around 3,000 Kelvin. Now, if you go measure the CMB, it's more like 2.7, saying that the energy in all of those photons has been reduced by a factor of 1,000. And that's a lot of photons. That's a lot of energy. It's gone. And if you think to yourself, well, maybe that's the dark energy, people have thought about that. It just doesn't compute, right? So here's an example where that Einstein equation and the expansion of the universe just doesn't add up to energy conservation at all. Okay. So again, here's the kind of problem that Hilbert assigned to Emmy Noether to take a look at. Now, unfortunately for Emmy, I guess, she wasn't up on Hamiltonian dynamics, and solving her problem is actually fairly easy if you think about it from the point of view of Hamiltonian dynamics as opposed to the Lagrangian dynamics that she was working with. I don't know if everyone here has got far enough into the idea of Hamiltonians and Lagrangians to know about this, and also the Poisson bracket. The mathematician Poisson came up with this idea of brackets, and the curly bracket here indicates that where you're doing A bracket B, you take the partial with respect to x of A, then the partial of momentum with respect to P, B, and then do it the other way around, subtract the two, right? And the very, very pretty answer is that if you do a bracket with, say, momentum and the Hamiltonian, which is the total energy in a system. So a Hamiltonian is the kinetic energy plus the potential energy. It turns out that whatever physical parameter you're bracketing with the Hamiltonian, what you get out is the time derivative of that parameter. So x bracket h turns out to be x dot dx by dt. P bracket h turns out to be p dot dp by dt, which is force, right? So for any function q, if q dot equals 0, then q bracket h equals 0. And when you take x and p and bracket those, you get 1. So X bracket P is 1, P bracket P equals 0, and this is what you see in the Heisenberg uncertainty principle when you're doing, the quantum mechanical bracket is, in a sense, derivative of the Poisson brackets. So you can say here that P is the generator of spatial transition, L, angular momentum, is the generator of rotational momentum. But the Poisson brackets, just like the modern quantum mechanical brackets, are anti-symmetric. And what this says is that if P bracket H is 0, then you have a flow of P that's conserved under the flow generated by H, going back to, what you and I were talking about earlier. And also H bracket P has to be equal to 0 because of this anti-symmetric concept. And so P dot H implies that H is invariant under spatial translation. This is the first Noether theorem. So you've got these two kinds of different ways of looking at the situation if Q bracket H is equal to 0. One way is that Q is constant along the flow of H, dQ by dt equals 0. The other way is that H is constant under the flow of Q. Q generates a symmetry of H, okay? Much simpler than the Lagrangian approach. But anyway, let's dive into that. So here's a minimal introduction to the concept of action. So we define a Lagrangian T minus V, and then we define an action as the integral of the Lagrangian from some starting time to some final time. Okay. Anyone in here already seen Lagrangians, Hamiltonians, or just okay? So S is the common symbol for action now, and we demand that the variation in action equals 0, or that it's stationary. Sometimes it's a minimum, sometimes it's a maximum, sometimes it's along a saddle point, depending on the situation. If you haven't dug into the variational principles of mechanics, I highly recommend this volume, Cornelius Langsos, on the variational principles of mechanics, in order to do the deep dive into the Lagrangian principle. In general, for particles or discrete objects, the kinetic energy is generally going to be a function of the time variation of the configuration variables, x. And the potential energy is typically a function of the configuration variables themselves. And so we will have a Lagrangian that depends on x dot and x in some way. Well, now we get into Noether. So in 1918, Noether published this paper in German, Invariante Variational Problems, and dedicated it to Felix Klein. I think his birthday was coming up. I think she must have been some sort of punster, because if you translate this into English, it's invariant variational problems. And if you haven't, got this, I highly recommend this book, The Noether Theorems by Yvette Kosman-Schwarzbach. It also has her first, this paper from 1918, but does a deep dive into the response in the mathematical and physics communities It was sort of forgotten after an initial splash, but only came up in the 1950s again when people started to get interested in the whole situation of symmetry groups in physics. And of course, that's about when gauge theory really took off. So some context before I go through the two theorems. Noether uses the symbol I instead of S for action. And she distinguishes between a finite continuous group with a certain number of parameters and then an infinite continuous group. So if you think back to that U1 phase, the circle, if we wrap the phase, for example, and we only think, well, okay, phase is going to be between 0 and 2 pi or plus pi and minus pi, then we have a finite symmetry group. If we think about, one of those photons that got released in the cosmic microwave background 3,700 years after the Big Bang, and it's been strolling towards us and our detectors for 13.7 billion years, the accumulated phase of that photon is kind of big, So think about that as an essentially infinite symmetry group. Of course, in a more, simple format, if we're thinking just about a finite symmetry group in space or time, then we're going to think about moving our experiment from here over to here, right? And so we have a finite but continuous symmetry group in terms of spatial variation or time variation. I do an experiment now or I do it tomorrow afternoon. So I'm moving a certain distance in time, okay? Well, so if you consider a Lagrangian, t is a function of momentum and u as a function of q. I'm going to use the more standard symbols for conjugate variables here. And we do a finite symmetry transformation of those two variables. And so let's say instead of L as a function of, or T as a function of P, I move it somehow in space or time, and I have a new function of momentum, call it U, and a new function of the configuration variable, call it R. Then the symmetry group demands that if delta S, the variation in that first Lagrangian, equals the Lagrangian or the integral of the Lagrangian with the transformation applied, they still have to equal 0. The variation in the Lagrangian under a symmetry group has to be the same no matter what. Okay, so this is one of the central principles of applying these Lie groups to the Lagrangian. Well, here are two theorems. So basically the first one, which is commonly known, if the action integral is invariant under a group, I don't know if you can see that G rho, but that's a finite symmetry group, okay, G rho. Then there are R linearly independent combinations among the Lagrangian expressions which become divergences, okay? Doesn't sound much like she's talking about symmetry groups or conservation at all. She's talking about divergences. And then, she says, okay, the converse is also true. The theorem would remain valid in case you had an infinite number of parameters in the situation, all the stars in the universe, all the quarks and all the stars in the universe, that sort of thing. Her second theorem says that if the action integral is invariant now under G infinity rho, so now we have an infinite symmetry group, in the second theorem. So the first is about finite symmetry. The second is about infinite symmetries. Then depending on arbitrary functions in order, derivatives up to an order sigma, then there are row identities in the Lagrangian expressions and their derivatives up to that order sigma. What is that about, right? What is she saying here, right? So when we move from finite symmetry groups to infinite symmetry groups, there's a change in the structure of what she's describing in the theorem. Let's get to it. Well, I think there's a bit of fun here. I don't know what you think, but Michelson-Morley, I assume you all know about the Michelson-Morley experiment. It's sort of famous in physics. They sought to find an asymmetry in the speed of light. They failed and instead discovered a universal symmetry, right? It's one of the biggest failures in physics, I think. Einstein came along and discovered a rule for that symmetry by identifying a space-time metric for what was going on with the speed of light, okay? He cured the problem of the velocity of space by sort of unifying space and time together, right? And when he continued that to non-inertial frames, he found a nonlinear space-time metric. But what that destroyed was a previous global symmetry that people had thought about. Time alone or space alone. Now you have space-time together with a unifying metric, but the symmetry of space and the symmetry of time disappear. And this is what we're going to look at, okay? So what about divergences and conservation? What is Emmy Noether talking about when she says that the Lagrangians in her first theorem are going to contain certain divergences? Well, maybe you've seen here enough of sort of electrodynamics to know that if you're tracking a charge density in a certain space, d rho by dt. So rho is a charge density. We're looking at d rho by dt, okay? Charge is flowing through a wire, you know, some area of space. Then there's an equation here that correlates the total net current. Now, net current is a vector flow, right? So it's going to move along like this. And d rho by dt is equal to the divergence of J, the divergence of the flow as a vector field, okay? So if, in fact, the divergence of J is 0, then charge is conserved. d rho by dt equals 0 if the divergence of J is 0. This is sort of a central point to this analysis, right? So what we're going to look for is a divergence-free flow. How do we get there? Well, without any loss of, generality here, I'm just going to ask you to think about a simple harmonic oscillator. Imagine a mass on a table. You hook it up with a spring to some fixed point. It's friction-free. You begin to, move that mass around. And the equation of this in Newtonian mechanics, F equals mx double dot, or F equals ma. And by Hooke's law, the spring constant is a restoring force, so we get that the force is equal to minus k, the spring constant, times the displacement of the mass, right? Simple. And we can separate this into two different equations. X dot, or the velocity, equals p by m, right? mv divided by m. And p dot, the force, dp by dt, equals, by Hooke's law, that minus kx, the restoring force, okay? So now we can think about a flow in what's called an extended phase space. It's extended because I've added the parameter of time to it. It's just a phase space if I just think about x and p together, right? Then it would be just a rotation like this, okay? But if I add t to it, now I have a formula for a flow in phase space. So this is the flow we're going to look at. So u dot, just running the dots through is x dot, p dot, t dot. And of course, t by dt is just 1. So we wind up with an equation for this flow in phase space as p over m minus kx and 1, right? Well, go back here, you will learn that this phase flow is an incompressible fluid. It doesn't get bigger, it doesn't get smaller in a conserved system, okay? I mean, if I throw in friction, then the phase sort of circles into a collection point. The mass stops moving. But if I have a truly frictionless system, energy is conserved, then the phase flow is going to look like this spiral, right? Now, since the phase fluid is incompressible, the divergence of this flow is 0, okay? And just, writing that out, we get partial by x, partial by p, partial by t, dotted into p over m minus kx and 1. That has to be 0 by definition, okay? But here comes the vector potential. That means that by a simple sleight of hand in vector calculus, u, that vector, has to equal the negative of a curl of something. Call it the a vector, okay? And a is a vector potential. Now, I'm going to propose to you that there's an alternative view of action here. And that is that the claim here is that the action S can equally be expressed as a line integral of that curl of the vector potential along the path. So that S equals, from the starting point of the path to the ending point of the path, A dotted into dr. Okay? See how that happens. Well, again, I've claimed that U is equal to P over M minus KX and 1, and that is equal to the negative curl of some other vector A. I'm going to claim that a solution to that is P, comma 0, comma the total energy. So that's an expression for the total energy there, P squared over 2M minus Kx squared over 2, the total kinetic and the total potential energy, right? And you say, well, Allan, where did you come up with that? The idea is gauge, okay? You can fix the gauge any old way you want. Now, what's the gauge got to do with this? Well, let's just work it through. I say here's a claim that S is equal to this A vector dotted into dr, okay? And my claim is that a suitable A vector here is P, comma 0, comma the negative of the total energy minus H. And I'm dotting that into dx, dp, dt over, a path, right? Well, if I take dt out, then I'm dotting p0 and the Hamiltonian into x dot, p dot, and 1. And when you work that out, what you get is px dot minus the total energy, now dt from the starting time to the final time. And what that gives you is the integral of t minus v by dt over the starting time to the final time, QED. Okay? So what this shows is that there's a relationship between the curl of A and the flow in extended phase space. Now, what's the idea of gauge here? Well, whenever you see an A vector in physics, there's always a question of a gauge, so-called, right? Where the gauge is the gradient of any old scalar field, because the curl of a gradient is always zero. So you always have a choice of so-called gauge when you're talking about a vector potential. And I'm going to skip over this. So if I choose any values for gauge to add to a vector potential, because the curl of that gradient is always zero, you can go ahead and add whatever suitable gauge you want. And how are we doing on time? I think I'm going to skip over this. Just you can take a look at this later, but what I'm doing here is selecting a sequence of scalar fields that add to the A vector to give that form that I expressed earlier. Okay? All right. So I invite you to take a look at that analysis yourself. But I want to do another trick here with some vector calculus. Jump ahead to this picture. So let's say that we have a certain path now in extended phase space, which is the true path of, for example, our little vector or harmonic oscillator, okay? And I'm subjecting that to a finite displacement in, say, either space or time, okay? So if the initial path is gamma, then the final path or the displaced path is gamma prime, okay? And subject to what I've done pushing this system either in space or time, I've changed the initial point and the final point, okay? But the path gamma and the path gamma prime have got to be the same actions. That's, the truth of this symmetry group applying to the Lagrangian. These two paths have to look the same. So we have now a kind of loop in extended phase space. So if I start at the initial point, I go across along the displacement of the initial values. I track the gamma prime. I get back following in the opposite direction the displacement in the final values, and then I track backwards along the initial gamma path. I've completed a loop, okay? So if we go back here, now I'm saying, well, okay, I have these flows along S1 and S2, the path in the two directions, right? And I showed before that that action is the A vector dotted into dr, and A, now here's another bit of vector mathematics in action. I can change the line integral around that loop into an areal integral dotted into the normal of that area that's wrapped around those flows, okay? But the curl of that is what happens when I make a change into the the integral over the area from the integral around the line, right? So I'm going for a loop integral on the one hand, dotted around the radius or the perimeter of this into an area integral within the loop, okay? And that means I have to take the curl of A dotted into the normal. But the curl of A is just the negative of the flow, right? So if I take a look at this again, the flow is gamma and gamma prime. And the normal to the area is just the line coming out of the screen. It has to be orthogonal to the flow. There is no area integral. It's zero, right? Whoops, I'm going back. ds over the area, u dotted into n, dA has to be zero. So the action around the loop has got to be net zero, okay? Now, what that says is that if the action gamma and gamma prime cancel out because they're equal, then SI and SF, those two displacements, have to be equal as well, equal and opposite, okay? Going along the initial shift in action and coming back have to be equal to zero. And voila, we have found something in this conserved flow in extended space, phase space, that is the equivalent of a charge. This is called a Noether charge, okay? And you see it when you compute the action along that initial displacement. So here, S of I is A dot into dr. And if you work that out for along that distance, you get the variation in P, the variation in X, the variation in time, dotted into P0 minus H, my proposal for that vector potential, okay? And as you see the computation, that comes out to be P times the variation in X minus H, the total energy, into the variation in time, okay? So if we're just doing a global and finite space translation, what we have is that the variation in time is zero, delta X is some constant, and then the Noether charge is a constant times the momentum. The momentum is conserved. Conversely, if you just do a variation in time and the variation in space, the configuration variable is zero, then delta t or del t is equal to a constant, and we have energy conservation. So this is the answer to what the divergence is in her first theorem. These divergences are going to either maintain momentum conservation or energy conservation. You also get conservation of angular momentum if you do this analysis in terms of in angular momentum. So much for the first theorem, okay? Let's turn our attention to the infinite variational groups. And so in quantum mechanics, or QFT, we're sort of beginning with an interest in the Schrodinger equation. I should have brought some water. How are we doing on time? So we have a wave function, and that's a complex function. It has a real and imaginary part. And if we used U1 symmetry and think about adding a global phase invariance to the wave function, then we would have on the one hand psi dotted into or multiplied by e to the I alpha, where alpha is some global phase shift, right? And for psi conjugate, we would be multiplying by e to the minus I alpha. And of course, since we can only observe the magnitude squared of the wave function, then that's okay because we're going to take psi times psi conjugate e to the I alpha times e to the minus alpha. It all goes away. Everything is, copacetic, right? And so that substitution works fine. But now, if we think about a completely random assignment, let's say, to the phase shift that we might apply here. Let's say instead of e to the I alpha, where alpha is a constant, I make it a function, the phase shift, a function of space. And so now I have sort of like this infinitely varying phase difference, and I'm throwing that at the wave function. What do I get now? Well, I get crap because the momentum operator throws del at psi, and now I get a momentum that is just jaggy everywhere, right? I'm totally making a mess of it. So what do we do to compensate for this idea of a global phase invariance to the wave function? Well, what we do is we come up with some redundant variables. And if we add q and the 4-vector A into this, and it's called the covariant derivative, you will see this expressed as capital D sub mu, the covariant derivative. What we recover is a wave function that works in quantum electrodynamics, okay? But this is Emmy Noether's second theorem to a T. If you go back at that, or to that, and read what happens with a global phase or symmetry group, what she's talking about is the introduction of otherwise redundant variables into the system. Now, this is a puzzlement if you think about it, because we solved a problem and we solved it beautifully. We introduced Q, the electron charge, and the A vector potential in, 4 space. And we're now using that in this modified equation. The question is, to a certain extent, why does that work? Why does this work, right? But this is exactly what Noether's second theorem says, and this is, by the way, introducing, in effect, an electron field, although, it's written down here as just a single electron. Stop thinking about the electron charge as 1.6 times 10 to the minus 19 coulombs. If you invert that, you just work out how many electrons there are in a coulomb of charge. It turns out to be Avogadro's number. And if you ever see Avogadro's number, you're doing chemistry, not physics. In physics, we just count them, okay? So think of this as in QFT, is just, you either have an electron somewhere or you don't have an electron somewhere. And the A field here is, in effect, the gauge boson for QED, the photon, okay? So here in curing a potential problem by adding an arbitrary phase to the wave function, we've found the electron field and its coupling to the gauge boson. Why do we call it a gauge boson? Because it's the A vector, and the A vector has a gauge. Okay? Now, Dirac, good old Paul Dirac, took this idea and, sort of jumped off a cliff with it. Here's the Lagrangian form for the Dirac equation, and, abandon hope, ye who enter here. What he threw in is this gamma mu, which is a set of spin tensors. And behind that, we've got on sort of the left side of the Lagrangian, the d mu and I q a mu. That's the kinetic energy. Minus m psi, the mass, is giving you the potential energy. And so again, it's T minus mu, but now we're integrating this Lagrangian overall spacetime, okay? So it's not just the simple, dt kind of thing. You're integrating overall spacetime to get this, but a ton of moving parts is hidden underneath this hood. And what we have here is the both an electron, but this also brings out the negative of the electron, or the positron, and the spin tensor, and the electron mass as a property of the essential, E equals mc squared property of the electron. Now, in order to do the full Lagrangian for quantum electrodynamics, we have to throw in this term at the end there, F sub mu nu times F mu nu up, which is basically bringing in the Maxwell equations hidden under those tensor equations there. Now, let's jump into quantum chromodynamics. SU3. So SU3 is the so-called special unitary group of order 3. Earlier on, I said that whenever you see S, what the special introduces is the idea that the matrices that are involved are pure reals. We couldn't have a pure real in U1, because if we didn't have the complex numbers, we wouldn't have phase, we wouldn't have anything. So S is not involved in the first quantum electrodynamic system, right? Now, but SU3, there's an 8-dimensional group of unitary matrices, which is to say that they have determinant 1 involved. And so that reduces the number of parameters in the otherwise 3 by 3 matrices to 8. So there are 8 so-called Gell-Mann matrices here. And they describe or give us the 8 gluons of the quantum chromodynamic system. So this system of 8 Gell-Mann matrices corresponds to the gluons of quantum chromodynamics. And this 8-dimensional system, now remember what I said before about the difference between a sphere and a ball? So this is an 8-sphere in an abstract space. So where U1 is just a first-dimensional sphere around a simple disk, in 2 dimensions. Now we've jumped to SU3 in 8 dimensions, and we're looking at an 8 sphere surrounding a 9 ball, if you like, right? And so this idea of rotations around this 8 sphere can be thought of as this third order matrices having 3 different kinds of color charges. Now, people say red, green, blue. It really doesn't matter. It's all subject to the relativity of put a pin in that 8 sphere and say that's red. And then you rotate around, you're going to find, blue and green. It's all, in effect, relative. But now here is the Lagrangian for quantum chromodynamics. And if you take a look at this and then compare it to quantum electrodynamics, you'll see that there are, no joke intended, certain symmetries. We have in quantum electrodynamics a gamma. We have this covariant derivative that couples into the fermion interaction with the A field, right? And here we have a coupling of the Gell-Mann matrices into the A field. We have a mass, and that, we have a Kronecker delta here coupling into the wave function, and then we also have the G sort of echo of the Maxwell equations for quantum chromodynamics, right? And so there's certain similarities between the whole idea of the Dirac equation for quantum electrodynamics and this equation for QCD, right? Although, not wanting to reduce QCD to QED by any stretch of the imagination, right? Well, now we get back to, the standard model, and I'm close to closure here. What are we doing on time? Running a little over. So again, we have U1 cross SU2 cross SU3, right? And looking over this, I apologize, but we just don't have time to deal with SU2. SU2 is a broken symmetry. It couples into the Higgs boson. You discover that there are 2 kinds of electrons depending on, this and that chirality. One interacts with a Higgs, one doesn't, blah, 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 blah. That's how we all get our mass. That would be another, 2 hours of digging into how SU2 is a broken symmetry. Sorry, anyone that loves neutrinos. I apologize here. Anyway, but I argue that outside of, the whole idea of the 3 generations of particles, which doesn't really, fall out of anywhere except truth. The first generation is where we live, and it's the up-down quarks, the electron, and the electron neutrino here as the fermions that we know and love. And then as far as the gauge bosons are concerned, the gamma is the gauge boson for QED. The 8 gluons are the gauge bosons for quantum chromodynamics, and the W and Z are the gauge bosons for the SU2, right? And you can just count them because, of course, the W and the Z are spinning out of the 4th order of SU2, so that would be a 2x2 matrix, but you impose a determinant of 1 on them, so you get 3. You get the W plus and minus and the Z, okay? So there's your three bosons that come out of SU2. If, hidden in here are certain ideas that couple into the idea of spin. So spin for spin 1, which is really 1, 0, -1, and spin 1/2, which is, plus and minus 1/2, don't really have to have couplings to any conserved flows. But if you've touched on supersymmetry at all or heard about supersymmetry, then a spin 3/2 fermion needs to be coupled into a conserved supersymmetric flow, and a spin 2 boson needs to be coupled into a conserved flow for the energy stress tensor. And if you're interested in that at all, take a look at physics stack exchange, blah, 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 all that stuff. And you'll find a kind of interesting analysis of where coupling into conserved flows and alternative spins come from. The coupling of the gauge 2 hypothetical gauge boson, or spin 2 gauge boson, coupling into the energy stress tensor, gives us a graviton, which is why the spin 2 boson would have to be a graviton. Anyway, just about done. So who was Emily? Let's go back to Emily. I think she was mistreated. She was born within a year or two of Albert Einstein. She was Jewish. Like Einstein, she had to flee Germany, came to the US. She got a position at Bryn Mawr teaching girls, because of course, girls. Einstein got a position at the Institute for Advanced Physics in Princeton, taught everybody. I understand that she was sort of a rough personality, but she's obviously brilliant. I mean, she went through all of that. And by the 1950s, again, pick up this volume if you're at all interested. Her work was basically rediscovered by everybody. Anyway, she passed away in 1935. Einstein, her contemporary, lived until 1955. Just saying, and that's it for me. Thank you very much for, paying attention to Emily Noether.
Thank you for this really interesting overview and introducing us or reintroducing us with Emmy Noether. We already are over time. Any real quick short questions, or otherwise we can certainly have private discussion after as well.
Yes, no.
One, we'll take one.
Long time ago, but was Amy's theory which explained the loss in the early universe. So
Is it what? I'm sorry, I didn't quite hear.
the early universe, when the universe started to expand, it lost heat, but it does not surround it.
So yeah, that's the basic idea. So Emmy Noether, maybe I didn't explain this very well. Emmy Noether was challenged to figure out what had gone wrong with energy conservation. What she proved here is that if you don't have a global symmetry, if you can't push time back indefinitely to, let's say, the Big Bang, or the expansion of space, then if there's no global symmetry, there is no energy conservation. So as space is expanding, like the problem with the cosmic microwave background radiation is that as space expands, the wavelength of all those CMB photons is equally expanding. E equals h nu, nu goes away, E goes away, right? And so that's the fundamental situation here, is that since the universe destroyed, the notion of global symmetry in space and time, subject to Einstein's general relativity theory, then there is no global energy conservation, global momentum conservation, right? That's, so if it was true that, I mean, if I could move a short distance here, then yeah, under these circumstances, we can talk about conservation of energy, right? I throw the ball up, the ball comes back down. But if I throw the ball towards infinity, all the bets are off, right?
Yes. Space-time and space of not, no?
I'm not quite sure I understand the space-time.
Space-time field. The field of space and time. The universe was expanding, so it wasn't fixed.
Oh, yeah, I see what you're saying. Yeah, I mean, something that was, a nanometer at 3,700 years after the Big Bang is not a nanometer anymore, right? Which is sort of the idea of gauge in another sense. Hermann Weyl, or Weil, tried to work on that concept in the time of special relativity. And his idea was, well, okay, maybe there's a force acting on the meter sticks, moving them around, and that was sort of, I mean, like people used the concept of gauge in the context of railroads back in the day. I mean, like gauge applied to the concept of gauge applied to the distance between the rails on a railroad,
Well, all right. Let's thank Allan again. So